Last talk for today, we have, I'm going to say your first name the French way, right? So Valentin Buciumas from the University of Amsterdam about Whittaker functions and p-adic groups and vertex models, please.
Thank you for the introduction. And I'd like to thank the organizers for organizing this, this very interesting workshop. It was a pleasure to be here for a weekend. So today I want to speak about some connections appearing in two a priori somewhat disconnected fields of math. So the first field is representation theory of p-adic groups. This is of great interest, especially to number theorists, but also to representation theorists or combinatorialists. And the second part is the theory of solvable lattice models or integrable lattice model. This is a theory that originated in physics, and eventually it was what led to the discovery of quantum groups. And people are very interested in things like this if they study, for example, quantum affine algebras or, for example, special functions. So yeah, so in the introduction, I'll just say a few buzzwords, nothing important, but I would like to first talk about a motivating example. So section 2 and 3 will be a simple example of what I'm trying to do. And I'll be very sketchy at times. So in particular, part of the motivation comes from this theory of automorphic forms. And I don't want to start defining a million things. So basically, I'll be sketchy. But I'll try to give a bit of motivation of why people are interested in Whittaker functions when they study representations of p-adic groups, and how this relates to solvable lattice model. And then in the very last section, I'll talk about some current results that are joint mostly with Ben Brubaker, Dan Bump, and Henry Gustafsson. There's a lot of slides before we get to the fifth section. So if I don't get it there, I don't think it's a big tragedy. So at least I hope to learn something from the first two. And I tend to sometimes get nervous and go through slides very fast. So if I do this today, you can feel free to stop me or ask any questions or comment on things if you wish. Okay, so on the left side of this connection, we have Whittaker functions on p-adic groups. They're actual functions on p-adic groups, and they satisfy an invariance property with respect to an idempotent subgroup. And the motivation mostly comes from number theory, from the theory of automorphic forms. So Whittaker functions are what's called, they appear as Fourier coefficients of some L functions. And if you study, for example, multiple Dirichlet series, the coefficients of those series will be values of metaplectic Whittaker functions. And we'll discuss metaplectic Whittaker functions later today if we have time. These multiple Dirichlet series are interesting because they allow you to compute certain moments of L functions. Okay, this is let me try the keyboard. So the goals for today is to study these Whittaker functions combinatorially and to prove some interesting identities about them. And the main tool that I will use today is the tool of solvable lattice models. Now, solvable lattice models are a different field. And what do I mean by solvable lattice models? I will always mean in this talk two-dimensional vertex models that can be studied using solutions of the Yang-Baxter equation. These first appeared in physics. And I think the first of these models was the six-vertex model, which was a way to model two-dimensional water atoms that formed ice. And some people, because of this, call it ice model. There is a connection to quantum groups and not invariants. So the solution to the Yang-Baxter equation that people use to study these models were formalized when people like Drinfeld and Jimbo came with the idea of a quantum group. These quantum groups were then used, for example, to build not invariants using things like using the work of Reshetikhin and Turayev. But before that, Jones could actually express certain not invariants, the Jones polynomial, by a partition function of a lattice model. Nowadays, many of these solvable or integrable lattice models are used to study special functions like Paul-Littlewood polynomials or McDonald polynomials or Jack polynomials. Any questions before we? So I have to go through some preliminaries for the theory of p-adic groups. I can work in greater generality, so I can say let F be a non-Archimedean local field, but I don't want to define that. So basically, let's just keep in mind the p-adic, the field of p-adic numbers. So this is F. It has a ring of integers, which is ZP. And I will denote the cardinality of the residue field by Q. So when I'm working with QP, Q is just equal to P. And in general, Q will be powers of P. And then I also need an uniformizer, which is an element in O. And when I'm working with ZP, that element will be just P as an element of ZP. But I want to make a clear distinction between Q and var pi. So I don't want to denote both of them by P. For the connection to integrable systems, I'll mostly be working with the group of invertible matrices over F. So this is GLR. But most of the things that I mentioned in this section about Whittaker functions hold in greater generality. So I could have worked with G like any reductive group that is split over F or something like this. And then of course I have to fix a torus, a Borel, a unipotent. So the torus is just the diagonal matrices in GLR. The Borel are the upper triangular, and the unipotent are the upper triangular with one on the. Okay, so now a definition is a Whittaker function is a function from G into C that satisfies a certain invariance property with respect to an additive character of the unipotent. So this is the most basic definition of what a Whittaker function means. I'm going to explicitly state what this character is. It satisfies some technical condition. But once this condition is satisfied, any character I take will produce more or less the same Whittaker function. So you might ask, is this definition dependent on the character? And after I impose some condition on the character, the definition will not be too dependent on the character. So this is a very general Whittaker function. And a subclass of Whittaker functions that are of interest are what's called unramified Whittaker functions. So besides this left n invariance, they also satisfy a right k invariance. So this means that Wg times k is equal to Wg for k in the maximum compact subgroup. They also are an eigenfunction of the spherical Heck algebra. So the spherical Heck algebra is made out of functions on G mod k. And this algebra acts by convolution on functions on G that are right k invariant. So I impose the condition that this W has to be right k invariant. So therefore the spherical algebra will act by convolution on it. And I want this Whittaker function to be an eigenvector. And these unramified Whittaker functions are important because they relate to unramified representations of p-adic groups. So in fact, you can build them from such representations. So for GLR, a tuple of non-zero complex numbers, an R tuple of non-zero complex numbers will determine an unramified character of the torus. And we can use this character to build an admissible smooth representation of the group. And we do this essentially by parabolical induction. And this representation is called the unramified principal series. It will have a unique spherical vector. That means a vector that is where the spherical subgroup acts trivially. And you will have a unique Whittaker functional. That means a function from the representation into C that is invariant with respect to n, left invariant. And then we can use these two objects, which are unique up to some factor, to build an unramified Whittaker function. So this is how you build all unramified Whittaker functions. And there is a formula for such functions, which is called the Castleman-Shalaika formula. So because of left and right invariance, the values of these unramified Whittaker functions will be determined by the values on var pi to the lambda for lambda dominant. So var pi to the lambda is just an element of the torus. So var pi to the lambda is just an element of the torus which has entries var pi to the lambda 1, var pi to the lambda 2, and so on. So once I understand these values, I understand all values of the Whittaker function. And a theorem by Shintani in the GLR case and Castleman and Shalaika in more generality gives you these values. So these values will be up to a quantum Val denominator. They will be equal to a Schur polynomial. So on the right, we have the Schur polynomial. Delta Q will be a deformed Val denominator. And then we also have a factor which makes some things easier to work with.
So the Z appearing here is the same as the Z that we used to build the
Yes.
whole series?
Yes. So all my Whittaker functions will implicitly depend on the Z. In this setup, it will be the Z that determines the character, which determines the principal series. And in this setup, it will be the eigenvalue of the spherical Hecke algebra. Okay, and there's a row appearing here, and the row will appear throughout the talk, and it is slightly different than the row most people use during this conference. So it's a bit shifted. So in particular, it starts from r-1 and goes all the way to 0. This is to make some computation slightly nicer. But you should think about it as the sum of the positive roots. Okay, so now I'll talk about a bit of the motivation of why number theorists care for these Whittaker functions. And I'll be very vague because I don't want to get into too much detail. But I would like to tell you two things. One is why they care about values of these Whittaker functions, and two, why they care about identities that these Whittaker functions might satisfy. So the ranking solvable method is a technique to construct a large class of L functions. And one way you can use it is to construct what's called the tensor product L function on GLR plus GLR. So an L function usually splits into an infinite product of L factors over all prime. And then you have maybe a real factor as well, but maybe that's not too important. In this particular case, it is a fact that the local L factor of this L function can be given as the inner up to some constant as the inner product between a Whittaker, an unramified Whittaker function and its contra-gradient Whittaker function. And this inner product will be an integral over GLR minus 1 mod NR minus 1 of values of these Whittaker functions. So W of G1, W tilde of G1 dg. We'd like to, for example, we would like to compute this integral. And as most p-adic integrals, this integral will basically become a sum, an infinite sum. And it will amount to sum of W of var pi to the lambda, W tilde of var pi to the lambda. Okay? So modular some constant in the front, which I don't want to talk about. We understand that this L factor will be equal to this sum. And now by the Castleman-Shalaika formula, this sum will be equal to a product of two Schur polynomials. And there's some other factors, factors which I'm kind of sweeping under the rug. And then finally, this sum just happens to be this product here. And this is what's called the Cauchy identity for Schur polynomials. So if you set Q equals 1, you get the regular Cauchy identity. And then it's not hard to prove this quantum version of the Cauchy identity from the regular one. The star factor comes from a Dedekind zeta function, but maybe let's not discuss that too much. But so what I want to point your attention to is that in this computation, two things were important, namely, as far as I'm concerned at the moment, namely, the Whittaker function appeared, and I wanted to understand its values on these diagonal elements. And then I wanted to understand how to compute this sum, which just happened to be easily computable using the Cauchy identity. So this is the moral from this first section, is that we should study Whittaker functions combinatorially, and we should use combinatorics to prove interesting identities. And one way to study Whittaker functions combinatorially is to use lattice models. Any questions before I go to lattice models?
I'm not familiar with the sure polynomials that you have beforehand, but they're highly dependent on the fact that you start with G of R, right?
Yes.
And in any other case where you have any other lead group or is specifying on computer, there's going to be an analog to
Yes.
S lambda, right?
So S lambda will be the character of the irreducible V lambda of the Lagrange dual group of G. So if I start with G over QP, the Cauchy formula tells you that you get some stuff times S lambda. So this S lambda here will be the character of V lambda, and V lambda is the irreducible of G Lagrange dual over C. The Lagrange dual of GLR is GLR. The Lagrange dual of SO2R plus 1 is SP2R, and vice versa. Okay, so this is the moral. Okay, so solvable lattice models. Again, by this I mean things that you can use the Yang-Baxter equation on. This motivated the work of the Leningrad and Kyoto schools, where people like Fadeev, Reshetik, and Jimbo and Miwa were working on these things. And eventually this led to the discovery of quantum groups. I think this was one of the main motivation for the discovery of quantum groups by Drinfeld and Jimbo. The most basic example of such a model is the 6-vertex model, which was used by Pauling to model interaction between atoms in ice. And it has several applications to other fields. And one of the most interesting applications that, in my opinion, is Kupperberg's application. So Kupperberg used a 6-vertex model to compute the number of n by n alternating sign matrices. This was proved, I think, maybe 2 years before he showed it, but the initial proof was very heavy combinatorics, and it was maybe like 130 pages long. And Kupperberg's proof is like maybe 15 pages, and it's very clear. Once you take a graduate class in solvable lattice models, you can understand it very easily. So it was kind of amazing that something like this could be done. So let me try to introduce a modified version of the 6-vertex model. So I'll consider a 2-dimensional rectangular grid. So that means I will have edges. So these things will be edges, and these things here will be, and the grid will be M times R. And I will denote the columns in the grid from 0 to all the way to N, and N can be anything, but usually it has to be large for this to make sense. And the rows will be denoted from 1 to R. Each row is assigned a parameter Zi that is a non-zero complex number, and we denote the rows from 3 to 1. Okay, so the idea in such a lattice model is that each edge will be assigned a spin, and the spin can be plus or minus. And there are two types of edges. There are exterior edges like this and this and this. And for the exterior edges, the spins will be fixed. And this is part of what's called the boundary condition. The interior edges, the spins will be allowed to vary. And a state will be an assignment of spins to these interior edges. So to understand what a state is, anyway, maybe I'll get back to this later. So first, let's talk about the boundary conditions. The boundary conditions will be as follows. The left and bottom boundary will be filled with spins plus. The right boundary will be filled with spins minus. The top boundary will have both plus and minus. There will be minus spins at columns that appear in the expansion of lambda plus rho. And there will be pluses everywhere else. So in this particular example, lambda is 3, 2, 0. Lambda plus rho is 5, 3, 2. So I have a minus on column 5, 3, and 0. We have Boltzmann weights. Boltzmann weights is an assignment of spins to each edge of, a Boltzmann weight is given an assignment of spins to each edge of a vertex. You assign to that assignment, you assign a value. So for example, the Boltzmann weight of this configuration plus is 1, and so on. And here we have only six configurations, and everything that's not in this table, the Boltzmann weight will be 0. And this is part of the reason why this is called the 6 vertex model, is because there are 6 non-zero weights. Okay, so these depend on some, let's say, quantum parameter V and on Z. Z will be the parameter associated to each row. So in particular, if I have such a configuration in the first row, the Boltzmann weight will be Z3. This is the Boltzmann weight of a vertex. A state is an assignment of spins to everything inside the model. And the Boltzmann weight of a state is the product of the weights of each vertex. And then the partition function, which encodes a lot of useful information about this system, is just the sum of the weights of all states over all states. So let's do an example. This is an example of a state. So as before, the top part, the top boundary condition is given by lambda plus rho, which is 5, 3, 0. Left and bottom are plus, right are minus signs. And this is an assignment of pins to the interior edges. So for this state, the Boltzmann weight will be this polynomial in Z1, Z2, Z3, and V. How can we see this? Basically, you have to go row by row, column by column, and compute each Boltzmann weight. So for example, the Boltzmann weight of this configuration is 1. The Boltzmann weight of this configuration is 1 minus V times Z3. This is 1 again. This is 1 minus V Z3. This is 1 and 1. So for the first row, we have this factor, and then so on and so forth.
You said that the states that did not appear in the table that we had previously were 0, right?
Yes.
So whenever a state like that
Yes.
appeared,
Yes.
the product.
So if I had something like a minus, minus, minus 0, then everything is 0 because I have a 0 times a bunch of other things. This reduces greatly the total number of states. So I take a dominant partition lambda, I add rho to it, and on the top I have minus spins at the entries of lambda plus rho. So in this particular case, lambda plus rho is 5, 3, 0. So I have zeros in column 5, 3, and 0, and everywhere else I have pluses. And there's a theorem of Brubaker, Bump, and Friedberg that the partition function of this model with these boundary conditions, so it will depend on Z, it will depend on lambda and on V. This will essentially be equal to the spherical, to the unramified Whittaker function when we set V to Q inverse. We have this equality. So now what can we do with it? We can do a few things with it. So I want to present two applications. The first is Tokyamas Theorem or Tokyamas formula, and the second is the Cauchy identity. So Tokyamas formula says the following thing, that the Whittaker function is a sum over, you can write that as a sum over strict Gelfand-Setzin patterns with top row lambda plus rho of some weight that can be written like this: 1 minus V to some S of t and minus V to L of t times X to some weight. Here, S of t will be the number of entries in the Gelfand-Setzin pattern that satisfy this strict inequality. L of t will be the number of entries that satisfy this equality. And the weight of t will be given by the difference between the sum over two rows. So let's do an example. I think the best thing to do now is an example. So let's say I have this Gelfand-Setzin pattern. The top row is 5, 3, 0, and then we have a 5, 2, and a 1. Compute S of t as follows. We start looking at 4. If 4 is strictly less than 5 and strictly larger than 3, I add 1. If 2 is strictly less than 3 and strictly larger than 0, I add another 1. And if 2 is strictly less than 4 and strictly less than 2, it is not, so I don't add another 1. So S of t will be 2. Now, L of t, you have to compare this with this. So 4 is not equal to 3, I don't add anything. 2 is not equal to 0, I don't add anything. 2 equals 2, so I add a 1. So L of t is 1. And the weight will be 2 minus 0 is 2. 4 plus 2 minus 2 is 4. 5 plus 3 plus 0 minus 4 plus 2 is 2. So essentially for this, And then we can go back and compute this term in the Tokuyama sum. And this term will exactly be equal to this term. And to prove Tokuyama, you can actually show that there is a weight preserving bijection between states in this model and strict Gelfand-Zeppelin patterns. And how to do that, you have to look at, so let's go to the next slide. Look at the minus signs, the position of the blue minus spins, which are here. So this is 5, 3, 0. Then this will be 4, 2, and this is 2. So the position of the blue spins in between the rows will essentially give you a Gelfand-Zeppelin pattern. Once you look at the weights, it's maybe not too hard to see this.
Okay, I don't know if you know about this, but what's a Gelfand?
What's a Gelfand-Zeppelin pattern? Yeah. So it's a set of integers that satisfy.
So what you put at the top for you was your weight vector.
Yeah. So at the top we'll have lambda plus rho, and on this row we'll have integers that satisfy. This has to be less than this, and this has to be larger than this. Now this has to be less than this. This has to be larger than this. Not straight.
So this is where you compute the point.
Yes.
Okay.
Yes. Good. And strict Gelfand-Zeppelin pattern means that this and this cannot be equal. This and this cannot be equal. This and this cannot be equal. And so, how am I doing on time?
You still have 15 minutes.
Oh, I'm going very slow. Okay, so this is the first application, and the second application is the Cauchy identity. So how do we use lattice models to prove Cauchy identities? Essentially, you have to come up with two lattice models. The first one, the lattice model, and its dual. And then you put them one on top of the other. So in this picture on the left, I'll have a standard lattice model on the bottom, and then a dual lattice model on top. So I want to compute the partition function of this object, but then I want to cut it in the middle. So if I cut it, what I get is I get that this partition function will be the sum over all possible boundary conditions here of the partition of the top model times the partition of the bottom model. By definition, if I choose my models correctly, on the right-hand side, I'll get lambda, sum of lambda times S lambda times S lambda. So this is the Schur polynomials. And then what I have to do is go back to the right and compute this partition function. And usually there are functional equations you can show that help you compute this. So if I'm able to compute this total partition function and show it equals this, then I get this equality.
I don't want to slow you down too much, but so there's previously we saw that like the way we could make things work in other cases was just change the group and it would change, like for example the Schur polynomials and everything.
Yeah.
Here you have a lattice model. And I don't see immediately how
the lattice model is a GLR thing only.
Okay, there are no analogs of this.
There are, but maybe I'll talk at the end.
Okay, good.
Lattice models are a very type-dependent object. So you usually do things for GLR or SLR first, and then you kind of think maybe you can do something for the symplectic group. But it's very rare that you have something that works in generality. Okay. So like I don't know anything for like the group of like GQ or something like that.
Okay, it's not necessarily like just the geometry of the lattice model. It's more complicated.
So this is how you prove Cauchy identities using lattice models. And I'm proving it for this particular model, which represents the Schur polynomial up to some factor. But essentially this trick can be used very generally. So you can prove Cauchy identities for Hall-Littlewood polynomials and many generalizations. Okay, any questions? Let's move slightly faster. So now I want to talk about solvability of lattice models. Solvability means that I have what's called an R matrix, which is a vertex that's slightly tilted. So this vertex will be an R matrix that satisfies the Yang-Baxter equation. The Yang-Baxter equation for me means that the partition functions of these two models are the same. You can think, so why do I call this the Yang-Baxter equation? You can think about partition depending on the boundary condition. You can think about these partition functions as entries in a matrix that maps V tensor W into W tensor V tensor V. And again, V tensor W into W tensor V tensor V. So this equality, if you write it algebraically, will become the well-known Yang-Baxter equation, R12, R13, R23 equals ... And this will be a parameterized version in the sense that we have parameters Z1, Z2, and Z1, Z2 inverse. No, go on. Or okay. Yeah. So a very basic question for such problems is, if I have a Yang-Baxter equation, what is the quantum group associated to it? What's interesting about this example is that this R matrix comes from the quantum supergroup UVFGL11 hat. This R, well, I like to call this the L matrix. This L matrix, we actually don't understand where it comes from. So we assume it comes from the same group, but from a more obscure representation. So when I say that this comes from this group, I mean it comes from this group with the what's called standard evaluation representation. So like the simplest representation of this group. Well, this one we don't really know. It was mostly combinatorially found. Any other questions?
Can you show us that R matrix as a matrix?
It's not written, but it's essentially the same as the UQ of SL2R matrix, but in the top right boundary, you replace Q by Q inverse.
So is it a limit of the Bellari's elliptic R matrix?
I'm not entirely sure. So maybe let's go on. Now I would like to go through the train argument very fast and try to explain how this is a very useful trick in this theory of lattice models. So what is the train argument? We start with a partition function like this. So let me point you to something before. In the Yang-Baxter equation, the following thing happens. This vertex moves to the right, and the parameters Z1 and Z2 get interchanged. That's the main idea of the Yang-Baxter equation. So now for the train argument, we start with a partition function like this. And what I can do is I can add an R matrix to the left. So I basically multiply this partition by the Boltzmann weight of this object. And I can show that this the partition function of this model is the same as the one of this model. So what I mean by this is, if I have pluses on the both pluses on the left of this R matrix, then these will be forced to be pluses because this is the only non-zero configuration. So I get here, and now I'm able to apply the Yang-Baxter equation, which does this. So it moves the R vertex to the right, and the Z1 and Z2 get interchanged. And then I apply it several times. And then at the very end, I end up with the R matrix on the right. So now the partition function of this object will be a different factor here, A22. And this will be the partition function of Z2, Z1. Okay, so basically I got the following functional equation that up to some factors, Z of Z1, Z2 will be equal to Z of Z2, Z1. If A11 were equal to A22, I would get that the partition function has to be symmetric.
Is the Boltzmann weights of this new kind of vertex the same as the Boltzmann weights of the other vertices, or are they different?
They're different.
So,
So A11 will look something like Q minus Z1, Z2 inverse Q inverse. And A22 will look like Q inverse, more or less, I think, plus minus some factors. So, and the idea is these functional equations many times will be enough or almost enough to characterize the partition function. So for example, if you simplify our model by sending Q to 0, no, Q inverse to 0, you get a model for the Schur polynomial. And what this tells you is that the partition function is symmetric. So once you know that the partition function is symmetric, and maybe you do a few more other things, it's not too hard to show that the partition function equals the Schur polynomial. Okay, so these were a few tricks from the theory of solvable lattice models. Do you have any question? No. How much time do I have?
Less and less. Well, you started late, so you have 6, 7 minutes.
6, 7 minutes. Okay, so let's see what we can do in 6 and 7 minutes. Some general results. Part of my work during the last 3 to 4 years has been to study Whittaker functions using these lattice models. And there are 3 big cases. So you can generalize the setup from before of the spherical or unramified Whittaker function to Ivahori Whittaker functions. These are Whittaker functions that are not right invariant under the spherical subgroup, but rather under the Ivahori. Or you can replace GLR by certain covers called metaplectic groups. And then for those groups, study again spherical Whittaker functions and then Ivahori Whittaker functions. And what's interesting is that the lattice model somehow match with the p-adic theory in this somehow very great generality. So for example, we find 3 lattice models, 3 new lattice models, and all of them are solvable. And they're solvable with our matrix provided by these quantum groups. So instead of GL11, we now work with GLN1 for metaplectic spherical, GL1R for Ivahori, and GLNR for metaplectic Ivahori.
So does that mean instead of those plus and minuses, you'll have basis vectors?
Yes, exactly. Exactly. So this is what I will go to right now. The Ivahori group is a subgroup of the spherical subgroup, which you can define like this. So now let's talk about the lattice model. So for the Ivahori model, what happens is spin minus will be replaced by a palette of R ordered colors. So instead of minus, we can have any of the R ordered colors. So now I have to tell you how the model is modified in the sense that what happens on the right where we had minuses, we'll now have colors. And the Whittaker function will depend on a Val group element, which is an element in SR. So initially the colors are ordered from top to bottom. So red goes to red larger than blue, larger than green. And then W acts by permutation on these colors. For example, if red is larger than blue, larger than green, I start with red, blue, green. And then if W is S1, S2, S3, I permute this to green, blue, red. On top, we still have colors where lambda plus rho intersects the columns. And then there will be a second Val group element, which is allowed to permute colors on top. This is because Ivahori Whittaker functions will not be determined just by values, will not be determined only at pi to the lambda, but rather at pi to the lambda times some element W that lives in the Val group, which you should think of as inside the spherical. Okay, this is the Ivahori subgroup. These are the Boltzmann weights which are colored. They are fermionic, meaning you cannot, on each vertical edge, you cannot have more than once the same color. So you can have a blue and a green, but you cannot have red 2 times on a vertical edge. You can obtain the weight of general vertex via fusion. And the weights are fermionic, as I mentioned. We have some applications which include combinatorial formulas for Ivahori Whittaker functions and relating them to non-symmetric McDonald polynomials. And so here's another interesting thing. you can replace Ivahori Whittaker function by what's called parahoric Whittaker function. So the Ivahori, you build it from using the Borel, but you can replace, in the definition of the Ivahori, you can replace the Borel by a parabolic subgroup corresponding to a levy. And then there are, like the lattice model from before, I can modify it to suit this setting. So what do I do? Essentially, I have to equate colors. So for example, this is a state in the lattice model for the parahoric Whittaker function, where the parahoric subgroup corresponds to the levy GL2 inside GL2 cross GL1 inside GL3. And if I take the extremal case where the levy is GL3 inside GL3, I equate all colors, so everything becomes red. And this gets me back to the spherical model from before. So let me go through some more pictures and I'll skip everything that has text in it. There are some more applications, mostly of combinatorial nature.
Is there a quantum group corresponding to those parahoric models?
No, so the R matrix is the same as in the Ivahoric setting. And for the outside, and for the inside, we don't know. I think that's the shortest answer. There are some connections to work of Borodin and Wheeler, but they're not exactly on the nodes. And I think Borodin and Wheeler, and maybe Agarwal.
How many vertices do you have now?
Because so it's a bit complicated. So the horizontal edges, you can have no color or one color. And the vertical edges, you can have sets of colors, but you cannot have the same color twice. So for the vertical, you could have nothing or blue and green or blue and green and red, but no two reds. So it's finite, but it's it gets big. Okay, so more, let's not define a metaplectic group, but let's say a metaplectic group is a certain generalization of a reductive group that is useful for studying like automorphic forms, L functions and stuff like this. Okay, so in the greatest generality, we have a quantum group where, sorry, we have a model where now we replace minus spins by colors, and we replace plus spins by what we call scholars. Scholars is basically a way of saying super color, because we want the color and the scholar to be somehow different. But both of them will be ordered. There will be R colors, which is R is the rank of GLR, and there will be N scholars, where N is the degree of the cover, the metaplectic cover. Quantum group is UQGL hat Rn. The model is again fermionic, which means we cannot lap colors vertically. We cannot overlap them vertically, but we can overlap scholars vertically. This is because the scholar lives in the odd part of the quantum group, and when you take an alternating sum of odd elements in the odd part of a module, they behave like you would take the symmetric sum somehow. So this statement is correct, even though we can. What I'm trying to say is that this statement is correct, even though I'm saying here that we can overlap scholars. And now the right boundary condition will depend on a W element. The left boundary condition will depend on theta, which tells you which Whittaker functional you're picking from the Whittaker model. So one of the main features of metaplectic groups is that Whittaker models are not unique. So in fact, you have a large number of Whittaker functionals you can work with. And this takes care of that. So here's a state in this most general model. So we have colors. Colors go down and to the right as before. And we have the dotted scholars, which go down and to the left. Again, there is a combinatorial way to build Boltzmann weights. Now there will be infinitely many Boltzmann weights because you can stack these scholars. Okay, so we have some. Okay, so this is the Ivahori model in the metaplectic setting. The spherical model, you just identify all colors and leave scholars the way they are. This is how you get the spherical model, just like before. we recover some theorems and we prove a few new theorems. One of them is Peter McNamara proved a certain generalization of Tokyamas formula for metaplectic Whittaker functions, which was very useful at the time because it showed that Whittaker functions appear in the definition of Val group multiple Dirichlet series, and it also allowed people to prove some results about those multiple Dirichlet series. So we get this result. We also prove some Cauchy identities, some branching rules, and some other combinatorial. Yeah. And then there is some work on the Ivahori-Whittaker side of Slava Naprenko, who uses our model to prove a generalization of McNamara's. Okay, so now let me add one last slide at the end that involves Schur-Wald dualities, because many people workshop talked about Schur-Wald dualities, so I thought I should have a slide with that as well, especially since it's possible to. So these dualities will be slightly more general in the sense that there's a way to go from p-adic groups to quantum groups. You have to take two steps, and the middle step is the Hecke algebra. So there's a theorem which already appeared in Stefan's talk, which is due to Borel and Kesselman, which tells you that there is an equivalence between the categories of smooth GLR reps generated by the Ivahori fixed vectors and the category of finite dimensional reps of the Ivahori Hecke algebra. And then there is a realization of usual Schur-Wald duality for quantum affine due to Chari and Presley. Now we can phrase it as it being that there's a tensor that goes from the category of finite dimensional reps of the affine Hecke algebra to some subcategory of the finite dimensional representations of the quantum group. This is not always an equivalent, but only when this inequality is satisfied. So now if you compose these two functors, you get a functor that goes from reps of p-adic groups to reps of quantum loop groups. And this composition has some interesting properties. So the unramified principal series will get mapped to a tensor product of evaluation representations of UV of SLM hat, and intertwining integrals, which are very useful G maps on the p-adic side, will be mapped to affine R matrices. In our work, what we do is we implicitly identify the Whittaker space of pi z in the metaplectic setting to this representation of UV of SLN hat. So a very vague way of saying this is that the Whittaker functor can be seen as a composition of the previous two functors. This is not technically correct, and it's mostly you shouldn't take it literally. But I think this can be used this can be made more exact than I've made it today, and it can be used to prove some interesting things. Yeah, and thank you, and sorry for going over time.
Does this last thing explain why the quantum group appears in the Lattice model?
Partly, but not completely. So the quantum group that appears in the model is UQ of GL Rn. So this group, you can represent it like a box. And here you have something like UQ of GL R. Here you have UQ of GL N. And here you have some other things. This last part explains this side of this box. And there is, I don't know of a good explanation for this side. And I don't know of any explanation for these two sides.
But this N here came from the cup, the metaplectic cup, right?
Yes.
But in this last slide, it N didn't have to do with the metaplectic cup.
No, but here for Chari Presley, I can go from the Hecke algebra to every M, and I choose M to be M. Yes. Yeah. So for example, I can still do this when M is less than R. Then it won't be an equivalence, but you know, it is what it is. And this gives you some interesting, I think, possibly it gives you some interesting applications. So for example, there is a well-known theorem that when N is 1, so in the reductive case, the Whittaker model is either one-dimensional or zero-dimensional. I think I can show that this is due to the fact that representations of the irreducible representations of the quantum loop group SL1, well, probably I should write GL1 here, but SL1 hat are 0 or 1 dimensional because it's
That relates to the 0 1-dimensional of what?
the Whittaker, when there is no metaplectic cover, the Whittaker model of an irreducible p-adic representation has dimension 0 or 1. For UQ of SL1 hat, the irreducibles will also have dimension 0 or 1. I think I think this can be shown that they're equivalent statements using kind of this thing.
At the start with your motivating example, you showed how this had something to do with L functions of p-adic groups, and then
yes.
much, but I'm asking about this. So we also showed that we had certain functional equations with respect to the partition functions of your lattice models.
Yes.
Using the diagram equation, which in turn will relate the Whittaker functions at certain values, which are related to ranking subgradient to the local factors.
Yeah.
Using those functional equations, if you go all around the loop, you deduce some important relation between, or functional equations with respect to the L functions.
It's a long way to go, but the answer is yes.
And it does work.
So, for example, this was done recently for not for L functions, but for multiple Dirichlet series. I can give you. So essentially, this connection is slightly new. So many things like these functional equations for multiple Dirichlet series or McNamara's theorem and so on were proved like maybe like 2 to 3 years before we started working on lattice models. And for many of these things, there are easy proofs using lattice models, but they are actually reproofs because they've been proved before. So there is a famous example. There is an Annals of Math book that is 136 pages that proves certain, essentially, equality of 2 ways of defining coefficients for multiple Dirichlet series. And this can be proved using lattice models in like 20 pages. It's a reproof, but yeah, it's somehow, if your interest is mainly combinatorial, sometimes the combinatorics can be hard, but these models can give you very easy proofs of these combinatorics.
I guess we really have to stop now. So let's thank you again.